Okay, hi and welcome back. So in today's video, we're sort of going to conclude our mini-series on differential equations. And in today's lecture, we're going to be looking at the variation of parameters method to solve non-homogeneous differential equations. So we've seen a lot of different things with differential equations, from Cauchy-Euler to undetermined coefficients. Today we're going to look at variation of parameters, which is quite powerful, and we'll contrast it with some other methods in just a moment. You might notice throughout this lecture I'm holding my phone. That's because I forgot my microphone once again, and I don't want to have to go back to get my microphone and come back because that would take like half an hour, and I'd rather just record this lecture. So that's what we're going to do. So let's jump into it. Variation of parameters will be used to solve our second order differential equations, non-homogeneous this time. And we've looked at undetermined coefficients, which did that. But this is going to be slightly different. You might prefer this method over the other one, but we'll get into it. So the main difference between the two is how we approach finding the particular solution of our differential equation. If you recall from undetermined coefficients, we first found the complementary solution for our differential equation by solving the homogeneous version of it. From there, we found a particular solution, and this was done by guessing. And this is a single solution to our differential equation, the non-homogeneous version. And using these two, we said that our final solution was the sum of the complementary and the particular. But the hard part was guessing our particular solution. We saw how to guess certain things, for example, polynomial right-hand sides. We guessed polynomial terms, and similar for trigonometric and other things. But as you might guess, there are limits as to what we can guess. That's where variation of parameters will come in handy. Because instead of relying on guessing to find our particular solution, we're going to use a formula. This formula, however, requires integration, and these integrals may not be so pleasant to solve, which is one of the drawbacks of variation of parameters. But that's the general idea. We'll find the complementary solution this time, and then we'll use the complementary solution in a formula to get our particular solution. So let's take a look at what the formula looks like. Okay, so this is the formula we're going to use. The particular solution in terms of t we'll use as our variable equals negative y1 of t times this integral plus y2 of t times this integral. And these integrands are very similar. The key difference is the first term here is y1 and here it's y2. So you can sort of think of these two terms swapping their places to get the second term. So now we just have to figure out, what does this notation mean? Unfortunately, we're not going to get into how this formula is derived. For now, we'll just accept it as being true, and in the future, maybe we can prove why this formula actually works. So what do all of these terms mean? Well, suppose we're faced with this sort of differential equation, a very generic second-order differential equation in terms of t, right? A of t y double prime plus b of t y prime plus c of t y equals g of t. So we'll denote g of t to be the right-hand side of our differential equation. And this need not be 0 because we're looking at non-homogeneous differential equations. So this is some sort of function of t. So that defines one of our terms. Next is y1 and y2. Well, if we were to take the homogeneous version of our differential equation and solve that, this is what our solution would look like. We've seen numerous times when solving these types of differential equations that our solution is the sum of two terms, rather the linear combination of two terms. So we're going to look at the particular terms of it and sort of ignore the variable coefficients they may have. So that will be y1 and y2. The last thing we have to define is what w is. We're applying some sort of function w on y1 and y2. W denotes something called the Wronskian. Let's define what the Wronskian is. Okay, so here we go. This is our definition of Wronskian. Handwriting got kind of funky towards the end, but let's just read over it. So we say if y1 of t and y2 of t are fundamental independent solutions to this differential equation, basically what we argued here, what y1 and y2 are, then the Wronskian of y1 of t and y2 of t, which we denote as this, w of y1 of t comma y2 of t, is the determinant of this matrix, where the first row is y1 of t and y2 of t, and the second row is the respective derivatives, y1 prime of t, y2 prime of t. Or equivalently, the Wronskian, when we compute the determinant, is equal to y1 of t, y2 prime of t, minus y1 prime of t, y2 prime of t. With this, we're all set to go. Everything in our equation is defined. We know how to compute everything. So that means we can compute the particular solution just by our complementary solution. So let's do a couple of problems and test it out. Okay, so basically what I've done is I've rewritten the Wronskian up here because we're going to be using that, and we're going to take a look at our first problem, which is this right here, y double prime plus 4y equals tangent of 2t. Of course, we can try to solve this using undetermined coefficients, but since this is a video on variation of parameters, let's use that. So for variation of parameters, there's seemingly two steps. First, we get our complementary solution, and then using our complementary solution, we chuck it into this formula here and get the particular solution and add them together. So to get the complementary solution, we have to consider the homogeneous version of this differential equation. Well, this is just a constant coefficient differential equation, which we've seen multiple times. So to solve this, we can guess y equals e to the kt, and then solve for k. So we can take the first and second derivatives, substitute it back into here. You get k squared e to the kt plus 4e to the kt equals 0. We can factor out an e to the kt. That gets multiplied with k squared plus 4. In order for this to be equal to 0, we need k squared plus 4 to be equal to 0. So that means k equals plus or minus 2i. And of course, from here, we throw it back into here, e to the 2it plus e to the negative 2it. But of course, that has imaginary parts to it, so we can use Euler's formula to make it a real value solution. And of course, this was all covered in our video on that. So the solution is y equals c1 sine of 2t plus c2 cosine of 2t. And that's our complementary solution. So now we can try to find our particular solution. For that, we need a bunch of these quantities. So I guess first of all, we can take a look at probably the easiest quantity, which is g of t. Remember that g of t is simply the right-hand side of our differential equation. So in this case, g of t equals tangent of 2t. The next parts that are easy to compute are y1 of t and y2 of t. Remember, those are the two fundamental independent parts of our solution to the homogeneous differential equation. In other words, they're the independent parts to our complementary solution. In this case, sine of 2t and cosine of 2t. We'll ignore the coefficients that appear in front of them because they're just constant values anyways. So we can say that y1 of t is equal to sine of 2t, and y2 of t is equal to cosine of 2t. The order of these two doesn't really matter. It's just one has to be one of them and the other has to be the other. And you'll see that there's like some sort of symmetry into this formula, so that takes account for how you could assign these differently. Okay, now we just have to compute the Wronskian, which is given up here. We have y1 of t and we have y2 of t. The only thing missing are the first derivative of y1 and the first derivative of y2. Well, if we have these right here, we can compute their first derivatives. So y1 prime of t, taking the first derivative of sine of 2t with respect to t, gives us 2 cosine of 2t. Doing a similar thing for y2 prime of t, taking the first derivative with respect to t, we get negative 2 sine of 2t. And now we can compute the Wronskian. Using that formula there, y1 of t times y2 prime of t gives us the product of this guy and this guy. So that'll be negative 2 sine squared of 2t. And then we subtract from that y2 times y1 prime of t. So the product of these two is 2 cosine squared of 2t. Well, this is fine, but it becomes even better when we factor out a 2. And now we see sine squared of 2t plus cosine squared of 2t equals 1. So this is just negative 2. So that's going to be our Wronskian. Now, we can get back to finding our particular solution because we have all of the values, we just need to substitute and compute the integrals. So let's do it. So basically, I'm just going to compute the two parts of it independently and then sum them together just to save a little bit of room and some thought process. So this is the first part of our particular solution. So let's just substitute with what we know. So just using these values that we've already computed, just substitute them back into here and hopefully we match. So hopefully when you substituted, you got something that looks like this. And now I'm just factoring out the negative 2, the negatives cancel, make this a fraction, and we're left with this integral right here. Okay, so how do we go about solving this integral? It kind of looks like a u substitution kind of thing, right? Like it's cosine tangent, hopefully something will cancel. Turns out that it's not. So we can rewrite tangent as sine over cosine. And now we see that cosine of 2t, they cancel. And we're just left with the integral of sine of 2t. So if you don't know the integral of sine of 2t, let's just briefly do it off to the side here. I'll use this board just because I want to use the other half of this board. So we're curious in solving the integral of sine of 2t. This can be done by u substitution. We'll let u equal to 2t, du equals 2 dt, or equivalently dt equals du over 2. So now when we change these variables to u, we get the integral of sine of u. dt is now du over 2. So this is the 1/2 integral of sine of u du. The integral of sine is negative cosine. And then we can substitute the u back in. So this is negative 1/2 cosine of 2t. And we'll leave off the plus c term for now. So this solves this first integral. So if we fully write this out, it's sine of 2t over 2 times that. So it should be negative 1/4 sine of 2t cosine of 2t. Cool. So now let's solve the second part. So this is what we're trying to solve for. Let's just substitute using what we have above. Okay, so hopefully we got something like this. How do we go about solving this integral? Again, you might be tempted to think u substitution. Not really. So we can expand this as sine over cosine. And you should get something like that, where tangent becomes sine over cosine, sine times sine is sine squared. And now, again, I'm probably thinking, oh, maybe I want to do u substitution. But if I use a cosine as my u, it'll only cancel with one of these sines, so I'll still be left with a sine, which isn't too fun. If I use sine, it won't cancel with this cosine, so that's also not going to work out. So what do we do from here? Trig identities. We'll use the fact that sine squared plus cosine squared equals 1. So that means sine squared equals 1 minus cosine squared of 2t. Now, everything here is in terms of cosines. And so we can split this into the difference of two fractions. We get something that looks like this. The cosine squared 2t and the cosine 2t, they partially cancel. So we can rewrite this as cosine of 2t. And 1 over cosine of 2t can be rewritten as secant of 2t. Okay, so now the question is, what's the integral of secant of 2t and what's the integral of cosine of 2t? And again, we can do them off to the side up here. Maybe I'll need a little bit more room. I'm not tall enough to reach this properly, so bear with me. Integral of secant of 2t, again, we can use u substitution with u equals to 2t. And just as before, this tells us dt equals du over 2. So now returning into here, we get the integral of secant of u times du over 2, which is 1/2 integral secant of u. Integral of secant is one that I always forgot, but I think this time I got it. This will be 1/2 natural log the absolute value secant of u plus tangent of u. And of course, we'll substitute u back in. And so that's our first part of our integral. So I'm going to start writing it out, but we're not yet complete. So now all that's left to solve for is the integral of cosine of 2t. This will be done just like before. U equals to 2t, dt equals du over 2. Substituting integral of cosine of u times du over 2. This will 1/2 the integral of cosine of u du. And integral of cosine is sine, so this is 1/2 sine of 2t. And this time we're subtracting it, so in here we do a minus 1/2 sine of 2t. So now we're very, very close. We've done a ton of stuff to compute our particular solution. We've computed the two parts of it. We just now have to sum it together. So in fact, I could just say this plus that, but let's just write it out, make it a little bit cleaner. Okay, so this is basically what we got. -1/4 sine 2t cosine 2t comes from there, which is this term right here. And then we add on the second part of our solution, which is this, which is that. Sorry, that. So let's just do some algebra and see what happens. I'm just going to rewrite this as negative sine of 2t cosine of 2t over 4. Then we can do some distribution here. So this is minus cosine of 2t times the natural log of this all of this over 4. And then distribute this into here, minus and minus becomes a plus. I'll just write it below. So it's plus sine 2t cosine 2t over 4. And we see that the first term and the last term cancel. So our particular solution is as follows. Finally, to get our overall solution, we take the sum of our complementary solution with our particular solution, and we get our final answer. There you go. That's the first example of variation of parameters. As you can see, it requires a ton of work, a lot of algebra and calculus, but the beauty of it is now we don't have to rely on guessing. We just need our complementary solution to find our overall solution. So that's our first example. Let's take a look at a couple more. Okay, so here we have our second example. And in the first example, the right-hand side was tangent of 2t, which felt like, oh, we could probably use undetermined coefficients for it, make some sort of trigonometric guess, and then find our particular solution that way. This is going to be a little bit more challenging to do undetermined coefficients, which is why we'll see that variation of parameters comes in quite handy. Of course, we need our complementary solution first, so we look at the homogeneous version of our differential equation. Again, this is a constant coefficient differential equation, so we'll guess y equals e to the kt and substitute. I'm just going to skip a bunch of steps. Factoring out an e to the kt, we get, in order for this to be equal to 0, this polynomial must be equal to 0, so you can solve for k and see k equals -2 or -1. This means our complementary solution is c1e to the -2t plus c2e to the -t. So now we'll look at finding our particular solution. And of course, we need a bunch of these quantities. So let's list them. G of t, I guess since we're using t's for everything, I'll just make this e to the x, e to the t. It's just a minor thing, but it just helps me out here. So g of t will be equal to this 1 over 1 plus e to the t. For y1 of t and y2 of t, we look at our complementary solution. So y1 of t is equal to e to the -2t, and y2 of t is equal to e to the -t. Lastly, for our Wronskian, we need the first derivative of y1 of t and y2 of t. So the first derivative of y1 is -2 e to the -2t, and the first derivative of y2 is -e to the -t. And now for our Wronskian, we just use the formula. So y1 times y2 prime, that's going to be interesting. So the like bases, but the exponents add, and then we subtract from that y2 times y1 prime. And this, like terms, equals e to the -3t. So now we can start solving for our particular solution. So again, let's take a look at the first term here, substitute, and see what we can do. So negative y1 of t is going to be -e to the -2t, and then we take the integral of everything else. And we're left with this. So there's a lot of fraction stuff going on here. So let's multiply the numerator and denominator both by 1 plus e over t. So that'll cancel with this, and in the numerator it's just e to the negative t. And in the denominator we have e to the negative 3t times 1 plus e to the t. But having a negative exponent in the bottom is equivalent to having a positive exponent in the top. So we can remove this and multiply it by e to the 3t. Those have like bases, so we can just add their exponents. And this is e to the 2t all over 1 plus e to the t. And now it's time for some calculus. And for me, I always turn to u substitution. And last time, it looked like we needed u substitution, but I said no. This time, it doesn't look like u substitution will work, because how is anything going to cancel? But in fact, it will work. So let's choose u to be 1 plus e to the t. du is equal to e to the t dt. So now substituting, the numerator will stay e to the 2t. The denominator will be u. dt is equal to du over e to the t. Well, this partially cancels with this. If we take e to the 2t divided by e to the t, that just leaves us with e to the t. So rewriting this, we have negative e to the negative 2t integral e to the t over u du. Well, how does that help us? Here we'll be a little bit sneaky. Remember that u equals 1 plus e to the t. So that means e to the t equals u minus 1. From there, we can substitute for e to the t. We'll substitute with u minus 1. And this is a lot easier to integrate because we can treat this as two separate fractions. As such, this is just 1, and now we take the integral and then substitute for u. So that's the first term of our integral. Let's solve the second term. And we'll just substitute everything from before. And maybe approach this similarly to before, where we multiply by 1 plus e to the t on both sides, and then bring this to the top. I'm just going to skip a bunch of the math because it's repetitive. Hopefully you get something like this. This looks a lot more friendly for u substitution. And, we can try it. Something like that. Do some substitution. Indeed, the e to the t's cancel. So it's just e to the negative t integral of 1 over u du, which is just e to the negative t ln of u, which is 1 plus e to the t. Cool. So that means combining these two, we get our particular solution. So from before, yc, the complementary solution, was that. And now for our particular solution, we have both parts to that sum, so we'll just add them together. And to get our final solution, we add everything. And there you go, that's our final solution. So again, it's just a ton of algebra, but all we need is the complementary solution. And we see this probably would not have been obtainable by simply just guessing and using undetermined coefficients. Let's see one last example. Okay, so one more example, which is this. And again, you're probably thinking to yourself, why can't we just use undetermined coefficients? Like, I've seen something like this before. Why can't I just use it? We're going to use it. So we'll see what happens. But first, of course, we need to find our complementary solution. For that, we consider the homogeneous differential equation and then solve it. I'm not going to waste anybody's time here. I'm just sort of going to give it to you. Boom, there's our complementary solution. We can move on with life. So we'll try it with undetermined coefficients first. So the way undetermined coefficients worked is we looked at our right-hand side and then inferred what our particular solution would look like. Here we see an exponential with 2t as the power, so we would guess that yp is equal to e to the 2t, but of course we consider any constant multiple of it. And then we took the derivatives and then solved for a. So y prime of p equals 2a e to the 2t, and y double prime is 4a e to the 2t. And now we can substitute back into here. Y double prime, this, minus 4y prime, plus 4y. And we set this equal to the right-hand side, e to the 2t. In doing so, we get this. And we'll notice that the left-hand side goes to 0, which means we can't solve for a. Does this mean that maybe we made a bad guess? Well, it's only logical that we guess this, right? Because it's an exponential, and that's what we were trained to guess. Or does maybe undetermined coefficients not work so well? That's probably what's going on. This is where we can resort to variation of parameters. So, of course, we need our quantities. G of t is the right-hand side. Y1 of t is going to be e to the 2t, which means y1 prime of t is 2e to the 2t. y2 of t is e to the t, so y2 prime of t is e to the t. y2 is te to the 2t. So that means y2 prime of t, you can use the product rule here. T times the derivative of e to the 2t is 2t e to the 2t, plus e to the 2t times the derivative of t is just e to the 2t. And now for the Wronskian, we take y1 of t times y2 prime of t. So this goes with this, and we'll get 2t e to the 4t plus e to the 4t. And then we subtract the product of these two. Notice that the first and the third term cancel. So the Wronskian is simply e to the 4t. Now it's all about calculating our particular solution. So let's do it. That's our equation. Let's substitute everything in. So we have something like this. E to the 2t times e to the 2t is e to the 4t, which cancels with this. And again, same thing happens here. So this is just equal to negative e to the 2t integral of t dt plus te to the 2t integral of dt. The integral of t is 1/2 t squared, so we can rewrite this as negative t squared e to the 2t all over 2. And the integral of dt is just t. So this is plus t squared e to the 2t. These two actually combine to give us t squared e to the 2t over 2. So that's our particular solution. And note that this confirms our hypothesis that we made the wrong guess during undetermined coefficients. We guessed this as our particular solution, which suggested that a must be a constant, but our actual particular solution does not necessarily have just a constant. Sure, it has the 1/2 e to the 2t, but there's this also variable t squared term, which we didn't account for in here. That would have been really hard to predict while guessing, which is why variation of parameters is so powerful. Now we just close out our solution. And there we go. Done. We've learned a ton in not only this video, but everything leading up to this video. From constant coefficient differential equations to Cauchy-Euler differential equations to undetermined coefficients to variation of parameters, you now have a full toolbox of things that you can use to solve these differential equations. Remember, there are drawbacks to each and every method that you use to solve these differential equations, but each has their own power, and this last problem clearly exemplifies why variation of parameters in some instances is more powerful than undetermined coefficients. But of course, this requires a lot more work. But at the end of the day, we only care about getting the right answer. I hope you enjoyed this mini-series on differential equations. I love differential equations, so it was a blast to teach it. And yeah, hopefully you learned another thing. As always, take care and see you in the future.